Good afternoon. After this introduction of Ralph about cryosphere, my talk will be a bit different. I will also look to Anthropocene because it is the title of the session, but I will make a step and I will be interested in vector-borne diseases during Anthropocene. Myself, I'm a paleoclimate modeler, so what I'm doing in disease, vector-borne disease, I will explain that to you. But first, I want to tell you that all this work has been done only because I met this guy, Cyril Caminade, who is an excellent epidemiologist and biologist, and also because I got a very good PhD called Affiliation. The next step is just a result published in PNAS by Cyril Caminade. And what is this plot showing to you? It's the 4 IR5 scenarios that you can recognize by their name, RCP 2.9, and then growing to 4 and 7 and 8.5. And what he did, he takes the result of these scenarios and he computes the dispersal of the malaria. How this is possible? For malaria, it is really very easy because there are many biological models of malaria, some sophisticated, other crude. And what this picture is showing you is that if you feed this biological model by climate change scenario towards the 21st century, a parameter that illustrates the extent of malaria is the length of the transmission season. If you increase that, you increase the extension of the malaria. It's not a research question. Malaria, it's 500,000 of African, mostly children, that died every year. In Europe, we get rid of it, but in Africa, it's not the case. So it's interesting to be able to diagnose what will happen with classical scenarios. So these slides show that if the response of the malaria, to be a little bit crude, will be the following. In the plain of West Africa, because the temperature will be too high, the mosquito will leave. And then where they will live in the eastern region, which is a plateau region, in which the climate will be much favorable. So the next slide is showing you the added populations that will be infected by the malaria in different regions of Africa: central, southern, western, and eastern. There are 3 time steps, and there is the difference for the different scenario, and we average the biological results. What do you see here? It's a bit difficult to see, but what is very important is that in Central Africa through time, there is not such a big difference. It is the same for Southern Africa. The difference is in the bottom, west and east. There is a large decrease over western, but a large increase versus eastern. So why is it important? It is eventually important because, unfortunately, the health system in Africa is such that we have to know before to try to prevent. Okay, now go to another story. The next slide. Because I'm coming from paleoclimate, I work a lot on Heinrich events and instabilities of the cryosphere. And as you know, the cryosphere has not a linear response to climate change. And this is very easy to illustrate. This is what I do here. Here, it is a sea level rise during the deglaciation. So you know that the sea level rise is 120 meters. But it's not a linear sea level rise, of course. There are plenty of events. So we know perfectly that the response of the cryosphere is completely non-linear. So because we have these classical scenarios that I already depicted, we were interested to know what will happen if we get an accelerated melting of the Greenland. Why? Because we are paleoclimate modelers, we know that during glacial period, where we get huge ice sheets over northern hemisphere, Heinrich events, they provide fresh water, and this fresh water directly impacts the monsoon and the IT season. By the way, this is a little bit a tribute to a paper of Molitsa in 28, which was showing exactly the response of the monsoon. But since that date, there are many papers that show that fresh water input has for consequences to change the ITCZ and to change the monsoon. So our idea was, this is the next slide, superimposed to the worst scenario, but unfortunately the most realistic, so RCP 8.5, we superimposed a partial melting, accelerated melting of Greenland. It is a real idealized simulation, is just to show what kind of response we have. So we put the freshwater southern of Greenland corresponding to 0.5 meters, 1 meters, 1 meters 5, and 3 meters, considering that the whole Greenland is 7 meters. So this corresponds to a freshwater which is about 0.11 for 0.5 meters to 0.66 for 3 meters, and which is most striking is that we did that for 50 years. That means we begin to melt 2020 partial, and we finish in 2017, and we stop. So the question is that, is in present-day conditions, that means interglacial, with a small ice sheet as Greenland, if we have such an accelerated melting, will it produce anything in the monsoon region? The next slide is the illustration of it did a lot. So this is the June-July precipitation over a box located on the Sahel in a region where a lot of the population is infeodated to monsoon. Their life depends on monsoon and on July and on summer precipitation. And what you see here, you see the RCP 8.5 evolution during the 21st century, and then you see the decrease corresponding to adding 0.5, 1, 1.5, and 3 meters of partial melting of Greenland. And you see a drastic drawdown of the precipitation. Such high that in fact it will drastically impact the agricultural area and the population. So the next slide is showing you something which is quite interesting. On the top slide you get the RR5 result for the summer monsoon in Africa. It is better, I have to say that, it's important. It is better for RR6. So what you see here, and look at the red which is RCP 8.5, you see that there is a very model-dependent response of the African monsoon towards the 21st century. Some models decrease, others increase. So the response to CO2 is very variable and model-dependent. Down you see the figure that you have already seen. That means that when you add fresh water over Greenland due to the partial melting of Greenland, you are sure that you will drastically change the monsoon. So the next slide is more important for this part. I am going back to the mosquito in 1 minute. So what is the impact of that? We made a multidisciplinary study with people specialized on agricultural and demography, and we see the fact that you don't have precipitation in summer in this region makes it lower than the threshold of precipitation you need to have sorghum or millet, which are the cultures that they are doing now. So there will be no more possibility to do anything, and they will leave. So the first curve, the A, corresponds to the loss of agricultural area. The B curves corresponds to the fact that people will move. The B curves is with a demography fixed to 2011, and the C curves is when you account for the demography that is embedded in the IPCC scenarios. So the conclusion of this study, published several years ago in PNAS, is the following. Many times when you think about Greenland melting exactly as Ralph showed in the previous talk, you think about sea level rise and you think about coastal migration. But in fact, if you get an accelerated melting of the Greenland, as depicted here, which is extreme, you will not touch only the coastal area, you will directly touch the monsoon in Africa. That means continental migration. So this is quite, I think, important to realize. Okay, now going back to the mosquito, the next slide. So we decided with Cyril that we will also test, superimposed to the RCP 8.5, the impact on vector-borne disease, malaria, of an accelerated melting of the Greenland. So With our simulation, we feed malaria models. So there are several malaria models, as I told you, and there are sophisticated and unsophisticated. So sophisticated, they can surely compute the population infected. So Vector and Livermore model are sophisticated model, and Miasma, Mara, and LLMDR0 are less sophisticated models. So I didn't show exactly the same parameter. In one case, I show the population directly infected. In the other, I show the LTS, which is the length of the transmission station. Why did I do that? Because the demography is not seriously accounted for in the non-sophisticated model. So this is why I show you a physical parameter or a health parameter, the LTS. Anyway, what you see here is that if there is an accelerated melting of the Greenland, it also impacts the dispersal of the malaria, but not towards the east where it's a little bit decreased, but more about the south and southern Africa. Okay, so this is why I think the next slide, this field is very important to go. Why? Because as you all know, vector-borne diseases is a very important problem. We have now in Europe dengue autochtone, that means that there is dengue not brought by the external, but just due to climate change. We have also Nile River fever. We have many different vector-borne diseases spreading all over Spain and Southern Europe. So it is a real problem. So what is the state of the art concerning this issue? There are only a few vector-borne diseases that has good biological model. For instance, malaria is one of them. I will show another case in the next slide. So there is first this problem of the fact that every vector-borne disease doesn't have a good model, and moreover, this model, biological model, has to be validated against data, and this is also very complex. So there is mainly three issues. The first is the scenario. We have to investigate classical scenario, but also threshold scenario. So I show one example, but there are several examples that has to be tested. The second point is that the third point is that in fact the state of the art of the biologic model are very different from one illness to the other. So we have also to develop new biologic model to do this kind of study. I will show you another example, which is not linked to human, but to cattle. This is the next slide. We validate with the ERA 5 analysis from 1980 to 2017 the Rift Valley fever. This is an illness that touches essentially the cattle and essentially the immature cattle due to abortion due to this insect. So there are two major vectors. Both are mosquito. One is IRS and the other one is Culex. It's not so important. What is important is that we have a good model and we are able to validate this model. This illness is called Rift Valley fever because before it was only occurring over the Rift Valley, but it's no more the case. So the first things to do is to calibrate the model over a continent as Africa. This is what we have done. And the next slide shows you that we are also sensitive to the oscillation of climate. That means that during that period of validation, of course, there is DMI, which is an oscillation in the Indian Ocean, and ENSO. And we can see that this oscillation of climate is, of course, captured by ERA, but impact also the dispersal of the Rift Valley fever. So you can see that for the DMI, it not directly impacts. There is a certain lag between the oscillation and the infection. And you see that the infection, because the Indian is in East Coast, touch first and mainly Ethiopia, but it takes time before the illness is declared, whereas ENSO is much more larger, the area, and it's quite sudden. You have not to wait to see the effect. So the conclusion is that I benefit from the invitation of Axel to discuss this point, because I strongly believe that it is an important point, and I also strongly believe that people like us, we are paleoclimate models, so we have a view at centennial to millennial scales, we know that some accident already occurred in the carbon cycle or in the cryosphere. So we are more aware about that the climatologists that are just looking to what will happen at the end of this century, which is normal. And so I think we should participate to this effort. Thank you very much.